Welcome back once again, and just kind of review from before. This is actually our Stargate coordinate system. I just finally decided, since I can't find anybody to make, you just tell me what kind of coordinate system this really is. I've just decided I need to coin my own term. Maybe I'll be famous or something, get myself in some book, whatever. Not that I care. But it's, good bragging rights if you ever go to some geek meeting or something like that. Okay, but anyways, yeah, so this is going to be, I'm going to call it this either Stargate coordinate system or maybe hyperspace coordinate system. I think the latter is probably more generic and probably maybe should suit a lot more applications. Okay, so anyways, I just want to get that coined word out there, and I'm going to get rid of that. And as far as this coordinate system is going, we're probably not going to talk about it a lot more later because it's pretty much done. As long as we understand that, that's really all we need to know. Okay, now for the next thing what we're going to do is we're going to talk about distance calculations. Obviously, just like a radio, if you want to broadcast your radio signal from, let's say, New York to Beijing, or from New York to Moscow, you need a certain amount of power, okay? And in terms of a wormhole going a certain distance, there is a certain amount of energy that will be required. Quite a bit, actually. It's doable, but as we'll find out here. Okay, well, with that aside, what I want to tell you about first is, well, let me just kind of draw a circle on the blackboard here. Notice my circles are getting better. Okay, let's imagine that this is our polygon with nearly an infinite number of sides. Okay. And the one thing I want to let you know about these polygons, these circles, or whatever you want to distinguish them as I said before, okay, if this is the Cartesian coordinate system here, this is our y, this is our x lines. Our little arrows there can go to anywhere. One thing that we talked about before is that the more number of sides to the polygon, the more number of possibilities of places that you can actually get to in the Stargate system that are not at 0, 0. Okay. Unless we're just going straight in a straight linear line, we want to stay away from 0, 0. Of course, the only exception might be is if you're turning on a hyperdrive and you're just trying to jump a linear distance through space. If that's the case, then I suppose 0, 0 is fine, but this is a Stargate or wormhole, and so we want something different. Okay, but moving on from that, what I just want to say is, no matter how many number of sides you have to this polygon, you can never get outside the polygon, and this is a problem. This is a problem. Okay. But it's not really a problem if you really understand what's happening here. As we know from a lot of other recent famous physicists, everything around us is a fractal. Everything can be accessed by understanding fractals. All right. And this is what I'm going to be talking to you about first, how to access that next fractal level. Okay. So yeah, we can never, by putting in a certain address into this wormhole or Stargate device, we can never get outside of this boundary layer, okay? But there's always a way to break the rule, okay? And this is how we're going to do it. Okay, let's say this is planet B. This is planet A. Okay, our Stargate or wormhole device is at planet A. Okay, we want to get from planet A to planet B, obviously. So, what is the distance? What is the distance from planet A to planet B? Just as an arbitrary number, or variable, I want to say. Let's just call this C. The distance is C. Okay? Now, it takes a certain amount of energy to turn on a wormhole device to get a stable vortex. Okay? Now, imagine this is the size of the wormhole, right here, the size of the wormhole device. Okay, now if we want to get from here to here, we need to take the initial amount of energy it takes to turn on this device, to create a stable wormhole, and we need to put that amount of energy multiple times. We're like stacking energy levels up, like these different colors here. Okay, so we have 1, 2, 3, 4, and a little bit more. Okay. Okay, so the energy that this requires to turn on is one variable. Okay. The distance between here and here is another variable. Okay. And the other variable that we have here is going to be the radius of the Stargate. Okay. And these are really the only things that we need to really understand about. Okay. So now that you know, okay, if it takes X amount of energy to turn on the device, and it's 1, 2, 3, 4 times the distance of the Stargate diameter, or the radius squared here, then we need 4 times the amount of energy as it needs to turn it on to get to point B. All right, easy enough? Should be. Very, very, very simple. Okay, so without any other hesitation, I'm just going to go ahead and write this nasty equation out. It looks nasty. It's not really nasty. Let's see. Okay, so this is what we have here. It may look a little complex and so on, but no, it's really not. Okay, we have 2 times r. Like the dot in there for some of you to see. Okay, and then we have the square root of x1 minus x2, y1 minus y2, z1 minus z2. Okay, if you don't recognize this little equation here, this is just the distance formula between 2 points. Generally, if we're just talking about 2D, we don't even write this z1 minus z2 blah blah blah. Okay, but yeah, this is just the distance between 2 points in 3D space. Very simple. Over 2r, and this is one number. Okay. And then we're multiplying all of this by I. Okay? And let me explain what this is. And all this is going to equal to E. Alright? Okay, I is going to be, that really is just the initial amount of energy that you need to turn on the wormhole device, Stargate, to create a stable vortex, stable wormhole. Okay. And this is all this is the energy calculation. This is how much energy in joules it's going to require. Okay. Now, if you actually take and calculate this out, let's just say even you have a 1 foot Stargate wormhole device, and maybe it just takes 1 amp, or maybe I don't know, 100 amps to do this. It's going to come up to a lot of energy. Okay. Okay, but remember the initial introduction I did about the Stargate? I'm telling you, I already told you, it is not a pulsed DC device. It is an alternating sine wave going through these coils of the Stargate. Okay, so this equation just assumes pulsed DC or constant continuous wave. But it's not. So this actual equation is a little wrong. And I just made the same mistake that Einstein did about the entire quantity of energy in the universe. Didn't account for rotational speed. Because obviously, if we're talking about an energy that's circulating through these coils, and it's an AC waveform, then where's the frequency? Okay, because the faster the frequency, the more current is going to be generated. Okay, so we need to divide all of this by F is our frequency. F is the frequency, rotational speed of the energy in the Stargate. Okay. That was a very ironic bell as I just finished this equation, explaining it. Okay, so there you have it. That's the energy requirement of a Stargate device, of any wormhole device between point A and point B. Okay, so now if let's go into this equation a little bit more. Let's say we get this energy spinning at frequency of F. What's that going to do on a materials level? And that really is just going to mean